CH3u chemistry.
Yeah.
Don't forget to hit like and subscribe. No, oh good God, no. I could make like a logo and maybe like. Today's episode is brought to you by Squarespace. I don't know if you guys listen to podcasts, but if you're a podcast listener, it's like Squarespace, Blue Ribbon, or Blue Apron. Is that the food? What? There's like 4 companies that like sponsor every podcast. It seems like, and you hear the same ad like over and over again. Anyway, yesterday we talked about ionic compounds, and we said it takes a polar solvent to dissolve them, and when they dissolve, what do they have to do? Like we said, for it to work, looking at sodium chloride as an example, sodium chloride is normally all clumped together, right? The positives stick to the negatives, and it makes a crystal structure. Water is obviously free-flowing, but in water's case, the slightly negative side of it, which is the oxygen side, because it has a higher electronegativity, right, wants to hang out around the positive side of other water molecules, because opposite charges attract. Well, for this to get dissolved in there, it has to do what? It has to break apart. And the negatively charged ions are going to end up around the positive side of the molecule, and the positive ions will end up around the negative charge. Right? So it has to split up. Does anyone remember the word I used yesterday for that? Yeah, not disassociate, but dissociate. All right, so when ionic compounds dissolve in water, they don't just dissolve, they dissociate. In other words, normally, don't write this. Okay, so I'm about to write. Is everyone listening? Do not write this. So normally we would have just said if we put magnesium sulfate and put it in water, we get magnesium sulfate aqueous, right? And that's true. That is true, but it is a, oh, okay, yes, definitely. But it's really a simplification, because what that aqueous means is that this is actually going to split up into its ions. Now, not its individual atoms, its ions. What are the 2 ions in magnesium sulfate? Magnesium, good, which is Mg. What charge does magnesium take? Very good. Right? Because now that it's an ion on its own, and this is something we've never had to do before, as an ion all by itself, it has a charge in that water, right? That's why it's dissolving. And what else will I get here? Now, is the sulfur going to be on its own? Sulfur is stuck to 4 oxygens. And what do we call sulfur stuck to 4 oxygens? Very good. So we'll get the sulfate ion. And how do I write that? SO4, aqueous. And does it take a charge? Well, we can actually, if we know magnesium's 2+, we can just tell from this it must be 2-, right? This is only one of them. That make sense? Okay. Now, this is not to say that writing MgSO4 aqueous would be wrong. That's perfectly acceptable. But another way we can show it is actually to be more detailed, like this, down to its individual ions when we dissolve it in water. Who can tell me? Well, actually, you take a minute. Everyone take a minute and do the next one. Tell me what the ionic equation would be of dissolving H2SO4 in water. Yeah, definitely. Just to be clear, that 2 is not part of the equation. It's just like example 1, example 2. Yeah, when I looked up, I thought it was at first 2, and I'm like, no. I was just saying example 2. Off-sprinkle doesn't matter because we're talking about ions here. Okay. Yeah, it's not going to be hydrogen gas in the water. any more than it's magnesium metal in the water. Because if it were magnesium metal in the water, it wouldn't have a charge. Okay, don't gloat. We don't gloat.
She does.
I mean, I gloat, but you don't gloat. That's not a good trait to have, being a gloater.
Don't gloat.
So what are the ions here? I mean, one of them is the same, right? The SO4. So you can just put that. You know, we have that. And then what are we going to get out front? We're going to get hydrogen. And this is a weird case where I know hydrogen is normally a Hofbrinkel, and I'm always yelling like, it's a Hofbrinkel, but it's not here because it's not hydrogen gas. It's just the hydrogen ion. And the hydrogen ion is just H+. Now, we do have two of them, but that two is actually going to go in front. That's the one thing that makes this a little confusing. What that means is that those H pluses aren't stuck together. They're free floating. They can go wherever they want.
Okay. The rest of
I don't know.
Yeah. Yes.
How does that make sense?
Okay,
How does it
so
dissolve in water?
okay, so what this really looks like. This is a little esoteric, but that's okay. If sulfur is green, you don't have to draw this, but you can. And oxygen is red. The first thing you'll note is that sulfur, by the rules you know for ionic covalent compounds, should only be able to make 2 bonds. But in this case, it makes 4, which you'll learn all about if you take grade 12 chemistry, why it's able to do that sometimes. But this is SO4. And SO4 has a charge of 2-. Okay? And H2SO4 means, I shouldn't use the same color again. That's dumb. What do we want to use for hydrogen? I'm thinking yellow.
I thought yellow was something.
And you were right, and I was wrong, and now apparently we need to discuss that. All right, and then we have these hydrogen ions, and they're positive. Does that make sense? And when this thing is a solid, that's what it looks like. Does that kind of make sense? When you dissolve it in water, now when you dissolve it in water, you have Windows features ready to update. When you dissolve it in water, this can float freely, and it's going to go around the water. And what side of the water is it going to want if it's negative? Yeah, and which side of the water is positive again?
Hydrogen.
The hydrogen side. So it's going to hang out on the hydrogen side of a bunch of water molecules. Oh, that's not water. Now, the 2 H's that were stuck to it, they're still ions. Where are they going to hang out? They're going to want to be on the oxygen side, right? Now, keep in mind, they don't have to go together. I know that we say, but hydrogen's diatomic. It always sticks together. But that's hydrogen gas. We're not talking about hydrogen ions when we say it's diatomic. We're talking about hydrogen gas. The ions, not only are they not stuck together, they don't want to stick together because they both have what charge? Positive. And do 2 things with the same charge want to stick together?
No.
No. So hydrogen gas works because they share electrons, and that makes a covalent bond. But hydrogen ions have no electrons. You know, they've had the electrons, they gave their electrons away to make that ionic bond in the first place. Now they're both positively charged. And 2 positively charged things do not want to stick together. That's right. That's right. They're like siblings that don't get along. So we're going to get H+ ions here, and we're going to get SO4 ions here. Now the only thing we have to note is how many H+ ions are there? There's 2 of them. Is that a little weird? You do have to, when we're talking about ionic compounds, you do have to remember that the Hofbrinkel rule, the diatomic rule, doesn't apply. When we're talking about diatomic, we're talking about these things in their elemental stage, right? Just like how normally we would never write magnesium with a 2+ charge, we'd always be like, oh no, magnesium when it's on its own is just a metal. We don't write its charge, right? But here it's actually the magnesium ions that we're interested in. And its electrons to sulfate, so it has a 2+ charge now. Hydrogen has given its electron to sulfate, so it has a +1 charge now. Questions about that? Because we're going to use that to do some more interesting stuff going on, so I want to make sure that makes sense. Do you want me to give you one more example to try? Would that be helpful? Let's do one more example. Let's say dissolving calcium nitride. So calcium nitride, calcium has a 2+ charge. Nitrogen has a 3- charge, so it would be that. So let's dissolve that in water. We'll call that example 2B. Or not 2B, I don't know. We'll do something else. Yeah. Like aqueous?
Yeah, aqueous. Like, please think of Mr. Orlando with nothing but a aqueous. I think about aqueous. My brain is not good. I think
And now, you can use the other periodic table that has the ionic charges on it. Because you don't have to know them off the top of your head. I'm not expecting you to memorize them. So what charge does calcium also have? Perfect. So you're going to get calcium, and it's going to be its ion. So it's going to be 2+. And now, how many of them do you have? So that's different going front. Because they're not stuck together. When they were not dissolved, they were stuck together. Now, and then what charge does nitrogen take? Great. So you can put nitrogen 3-. And how many of them do we have? And again, nickel, it's going to go in front. And that number being in front is meaningful. What that means is those nitrogen ions are not stuck together. When they were solid, they stuck together. But now, they can flow over everything. Does that make sense? Yeah. Excellent. Okay, so let's talk about this one. When we dissolve calcium nitrate in water, is this calcium nitrate? It's calcium nitride. Good. Sorry about that. When we dissolve this in water, when it's a solid, those charges hold this thing together. So calcium's positive charge, nitrogen's negative charge, boom, they're stuck together. It's a really strong bond. When we put them in water, now there's charges everywhere, and they don't have to stick to each other. They can stick to the waters and float around. Right? It's like catching a ride. It's like in Back to the Future when he's on the skateboard and he like holds onto the back of the car. Yeah. That's really what these ions can do. They can just stick to water and float around with that water and then stick to this other water and go where it's going. It sounds like a really nice kind of free will and lifestyle. Like the California of chemistry. They just do what they like. How do I show that here?
Is that why you're called Orlando?
No, I'm called that because that was my father's last name. And we live in a patriarchal society where men are expected to keep their names through the course of their lives, and we expect women to just, kind of forget about their family history. But enough about the politics about Western naming practices. Yeah. So how do I show that here? How do I demonstrate that that these calcium ions and these nitrogen ions are now going to be free to float around? What do you got?
You put like EA.
Yeah, so I'm going to have calcium ions. What charge will those calcium ions have? Cool. What other ions do I have? Nitrogen ions. What charge will they all have? -3. Cool. Am I done? Oh yeah, you're right. They're aqueous. Cool. They're dissolved in water. balance, right? Now, the calcium, I used to put that 3 here to show that those 3 calciums were all stuck together. Are they stuck together now?
No.
Where's the 3 go? In front. Good. So that's not just semantic, it's meaningful. When we put a little subscript 3, that means they have to always, hey, they have to be stuck together. But when we put the 3 in front, welcome. Thanks. That's important because you know I've done my attendance already. Oh, wait. Which reminds me, I should do my attendance. And how many nitrogens do we, nitride ions do we have? Good, I like it.
No. Yeah, see, it's wearing a tutu.
Shh. Okay. How's that look? That looks good to me. Does anyone have any questions about that? Okay. Then what I'd like to do is this. I want to actually look at not just one compound, but what if we looked at, bless you, what if we looked at a whole reaction actually looking at what the ions do? Does that make sense? Yeah, that's fine. That's totally fine. Thank you. So before we get started, we need to do this reaction. This is a simple single displacement reaction. So take a moment and tell me what the products of this will be. You can put your hand up if you need some help, and I'll give you a hand. But go ahead and do this single displacement reaction. Nothing ionic, just how we've always done them. Just right up here. No, I don't want you to don't do anything you wouldn't have done. Pretend you were seeing this question a week ago. Just do it the way we've always done it. Yep.
The 2 in front of the NA is supposed to be like right next to it?
Yes, yeah, I have 2 of them. I've just pre-balanced the left side for you.
Is that 2 with the NA?
I've just pre-balanced the left side for you.
Okay.
You'd have had to put a 2 there eventually, so I beat you to it. Yeah.
Sodium is positive 1, right?
That's right.
Would LI be equals then?
Like when, on the other side?
Yeah.
No, you know how it always is. Single displacement reaction. You've done one, like you did one back there. When you got the copper off of it, was it aqueous? No, it was solid, right? This one is. This one is. Unless I've screwed up, but we're going to assume it is. Okay, so in a single displacement reaction, what's going to happen? What's going to happen? So we end up with sodium. And what charge does sodium take? +1. And carbonate has what charge? -2. So do I need more of any of these? Yeah, so I need 2 of these guys. Give me a sec. My brain is so feeble. I can't hear a conversation and do chemistry. It's too much. So how do I write this then? I need 2 sodiums, 1 carbonate. Great. That's going to be an aqueous compound. Anything with sodium is always aqueous. And what is now by itself? Solid lithium. Good. This is just like your copper and aluminum lab, right? Where aluminum displaced copper and copper chloride, and you end up with solid copper forming, right? So there we go. Yes, ma'am.
Would you have to put the 2 in front of that lithium?
Yeah, absolutely. Thank you. 100%. So there we go. So now we have a balanced chemical equation. But what I want to do is look at this as an ionic equation. All right? So what we are going to make right now is called an ionic equation. In fact, eerily, it's called a total ionic equation. We'll talk about what the total means in a minute. But here's the idea. everything that is aqueous, we write it together for convenience sake. And we will continue going forward in chemistry to write it together for convenience sake. It's a lot easier to say lithium carbonate aqueous than to say there's a bunch of lithium ions floating around. There's a bunch of carbonate ions floating around. But we know that for an ionic compound, as soon as this says aqueous, and again, only for an ionic compound, it means that these things aren't actually together. These lithium ions don't necessarily have to be anywhere near those carbonate ions because they can split apart and float freely. Does that make sense? So we write the reaction like this. It's appropriate. It's convenient. Yes, ma'am. Because L means liquid, which is different. If I took this and melted it, it would be a liquid. Aqueous means dissolved in water. So it means you've taken water and you've poured this into it and mixed it. And when we dissolve it, when we pour it in and mix it, those ions are able to break apart. That's a good question, by the way. It's an important question. It's an important distinction. Because liquid, right, like the water in this would be, you don't have to write this, it would be H2O liquid, right? It's not solid water. It's not gaseous water. But the lithium carbonate is dissolved in that water. It's put in and it's able to break apart. And the lithium ions have a positive charge. They're attracted to the oxygen side of water. The carbonate ions have a negative charge. They're attracted to the hydrogen side of water. And they're now floating around freely. And what we want to do to make an ionic equation is we have to split up all of the ionic compounds that are dissolved in water. So in this case, what are the ionic compounds that are dissolved in water that we have to split up? It's not a trick question, just what's dissolved in water in this reaction? Li2CO3 is dissolved in water, so it's going to actually be split apart. And sodium carbonate. Good. Yep, of course. So what I want to do, and we'll do this one together, is rewrite this equation, but with those ions split up. So this would be two solid sodiums. Anything that's solid is unaffected by this, right? But anything that's aqueous, we have to split up. So how do I split this up? So we have two lithium. And how do I show that these are ions, not just lithium metal? Yep, the charge. And what's the charge on lithium ions? +1. Good. And we're going to say that's dissolved in water. And what's the other ion? So we got the lithium. And we also need the carbonate. And that's CO3. And what charge does carbonate take again? -2. And that's also aqueous. And then on the right side, I now have to break this sodium carbonate apart to be ions. Did you say two? Nah. Okay, so yeah, we're going to have two sodium ions. Now again, how do I show that this isn't sodium metal? Yeah, and what charge does sodium take? +1. And I don't really need to put the 1, do I? That's cumbersome. And what's the other ion? Somebody else. Somebody else. What's my other ion here? Yeah. Very good. And what? Again, it's an ion, so I have to give it a charge. Great. And what have I not put in here yet that I really should? Very good. These are both aqueous. And am I done? No, I have to make sure I get the whole equation in there. So what's the other thing that's left? See, Lauren, ask and you shall receive.
Bonjour, class.
Oh, bonjour.
Bonjour, monsieur. Ça va bien? Merci beaucoup.
You go to Ruby High, if you look at the Instagram.
I didn't ask. I just want to walk and I'm going to beat him. I didn't bring him to that.
No. Everything that needs to be filled in. Yeah. So the streamer order is going in Monday night. So this isn't like any of your assignments, whatever you handed in Tuesday, and it's okay. There is no Tuesday. So there's no late marks on the assignment. You're either going to go through or you're not going to go through. Okay? Did you choose colors on the end? Because that was a flaw.
I want all three in one.
Okay.
Are you ready?
Like Monster High, but actually scary instead of funny. Oh, sorry, did I say that loud? I did the thinking part out loud again. Sorry about that. Yeah, because there are, how many of them? Yeah, and now here's the important thing. When the 2 is down below like this, that's meaningful. A 2 subscript means that they are stuck together. They're a compound. They have to be together. There's still 2 of them, so we can't change the balance of the equation. But now we can put it out front because each of those sodium ions is free to go wherever it likes. So they go from being stuck in a compound to being free and flowing. Oh yeah, very important. Otherwise it's not balanced. Well, then it wouldn't be balanced to this up here because we know from up here that there's 2 sodiums and 2 lithiums for every 1 carbonate. So you'd be changing the stoichiometry, you'd be changing the mass relationship, which we can't do. That's right. You should teach chemistry. That was good. That's really good. I'm going to practice that in the mirror tonight because your cake ain't going to rise. Because your cake ain't going to rise.
Rise because of baking soda?
Yeah. Oh, totally. See?
All right.
See? He's good.
Good talk.
And you guys know why, because baking soda is just calcium carbonate. And when you heat calcium carbonate, any carbonate decomposes to give you what? Huh? Why does your cake rise? Calcium carbonate, we heat it, we get what kind of reaction? The only reaction possible when we just have one thing. What's this going to do? Yeah, what do we call that kind of reaction when one thing separates into 2 things? Decomposition. And a decomposition of a carbonate always gives you CO2. And of course, what remains over here would be, well, we've taken the carbon, we've taken 2 of the oxygens. What's left? Calcium and oxygen. So we get calcium oxide. Cake's full of calcium oxide. And CO2. CO2 is, of course, the gas. Hey, you ever wonder why cake is like fluffy and beautiful and there's all those like little air pockets in it that makes it like not dense, like just a piece of dough, but like beautiful and fluffy? It's because as it's cooking, gas is forming all throughout it, which makes big holes in the dough. And then when you cook it, it's fluffy and lovely because baking is just chemistry that you can eat. Again, if we are able, that's exactly what we will do if we go quick enough through this next unit. We will have time to do our baking lab, which is tons of fun, let me tell you. But only if we have time. Okay, and then what's the thing left in this reaction? I didn't quite finish it. Yeah, we have 2 solid lithiums. Okay, there we go. This is the exact same reaction. It is just written as an ionic equation. Instead of writing a balanced chemical equation, we wrote what we call a total ionic equation. It is the same reaction. It's just a different way of expressing it. It's more accurate, but it's a pain in the butt to write it this way, so we typically don't. Yes? Ions have charges. So, like, again, you know this because if you touch a piece of copper metal, it doesn't electrocute you. It isn't charged. And I want to make a note. Don't forget that solid sodium and sodium ions aren't the same thing. They behave chemically very different. All right? One is elemental sodium. The other is a sodium ion. They're not the same thing. Okay. We then use something that is actually useful. The total ionic equation is like an intermediate step. It's true, it's accurate, but it's not useful. What I want you to do is rewrite that total ionic equation down here. So this reaction involves taking two sodium atoms that are happy little sodium metal atoms. But they react with lithium carbonate that's been dissolved in water. And when we dissolved that lithium carbonate in water, we got two lithium ions and a carbonate ion. Oh, those don't have a 2+ charge. That's a lie. And because it's a single displacement reaction, what actually happens is lithium two of them, and two sodium ions and a carbonate ion. Now, this is one of those moments where you get to realize that your science teachers have been lying to you.
I feel like there's a trend in this class.
Yeah, I'm exposing the lies. I'm like Penn and Teller.
But don't you
First I tell the
recognize
lies, then I expose the lies. So, true, it is like rounding. So, here's what I mean. We have always taught that like the metal has to be strong enough to kick out the other metal, right? Well, hopefully I was repeating whatever your grade 10 teacher taught you, because you learned single displacement reactions in grade 10. But yes, I have been a part of the complex of lies. But when we actually look at what happens here, it's more interesting. Don't forget that that lithium that we're quote unquote kicking out wasn't actually stuck to the carbonate. Right? We think of them as like they're on a date and you kick one out. It's a fun little analogy that helps us remember. But that's not how the chemistry actually works. When we dissolved that lithium carbonate, the lithium ions were floating freely and the carbonate ions were floating freely. They weren't actually together. Let's actually look at this reaction and think, there's something in this reaction that's just along for the ride, that doesn't do anything. What is it? What in this reaction starts out as one thing and stays the same thing at the end? Yeah. Yeah. What do we call that again? Well, yeah, the carbonate ion. If we look at our pal carbonate, at the beginning of the reaction, there are CO3 2- ions floating around in water. And at the end of reaction, there are CO3 2- ions floating around in water. Have they done anything in this reaction? No. They are what we call a spectator ion. So they are as involved in this reaction as I am involved in my son's hockey games. Which is to say I'm in the building. And occasionally I shout things like, try harder and do better. And you're walking home if you lose. You know, encouragement. No, I'm a hockey dad. And I see the other hockey dads and I say, how about that local sports team last night? That was quite the match, wasn't it? And they say, yeah. And I say, yeah. How about that national level sports team? Didn't they play a great tournament the other day against the other sports team? And then, yeah, like manly talk. We have manly talk. Sorry? No. No. Who told you that? Who told you that? We'll talk at lunch. Bring your money. So the carbonate ion isn't actually involved in this reaction. If we start with carbonate, we end with carbonate, nothing changes about that carbonate. I want to rewrite this reaction ignoring it because it's not actually doing anything. In other words, when you read the summary of last night's hockey game in the newspaper, because you all read newspapers every morning, it does not mention what the person sitting in section 115A, seat 23, ate for snack. It doesn't mention who had the most soda, who had the least soda, and you know, that guy forgot his wallet. It doesn't mention any of that because nobody cares about the spectators. with very few exceptions. Basically, if a spectator dies, they will get mentioned in the newspaper, or if they run across the surface of the playing field with no clothes on, they will be mentioned in the newspaper, and that's about it.
The way of the streaker has kind of gone.
Yeah, it's not a thing like it used to be, eh? Like, that used to be a regular occurrence, where you'd be watching a baseball game, and it's like, and that guy's got no clothes on, and he's running across.
Dorm window down
Yeah.
the courtyard. Oh my gosh.
Yeah.
You know, look at all these people.
Yeah, streaking used to be a real thing.
Yes.
Yeah, you don't see it so
Even a
much.
song about it.
Yeah. So,
Mr. Orlando, just
Yes.
in case you didn't check,
which I did not.
you're covering.
I
the
did know.
first half
Can
of
I
my
tell you,
series.
I have such a, there's this thing, I never check if I have coverages. And I am so lucky, something always comes up, or somebody will always mention like, oh, I see you're like, and not usually the teacher, you're being very responsible, but it'll always be like, oh, I see we're sharing a coverage now. I'll be like, I saw.
It'd be like that, eh?
So that was, Calford today was like, oh, we got music coverage today. And I'm like, oh yeah, I knew that. I totally read my emails.
But you know what? I'm going to tell you really quickly.
Yeah.
The grade 10s that are in there, all but Bradley Grocott,
Yeah.
are coming with me. So you
So it's going to be a small
only
group,
have
the
the
nines.
We are doing a scavenger hunt through the method book and writing skills. I'm sorry. I
That
just
sounds
would
really exciting.
rather-
They're going to love it.
They know about it. I've prepared them for a couple days. And I'm sorry, you know,
It's
like
fine.
it would have been guitar, but I don't want them taking the instruments out. We've got 7 percussion players. I think it's just going to be a nice quiet room. I've already.
Yeah, I'm sure it's going to be
Bradley
very
will-
quiet.
No, listen, he said he would help. I've already talked to Resource
fine.
about sending a couple people.
Okay,
down,
it's
and
fine.
Bradley said he would go and peer tutor.
It's fine.
There
Between
you go.
Calford and I, we know a lot of these kids. We'll be fine. We're actually doing we're going to be in there together the whole period because we're planning some
Oh, that's
activities.
right.
Yeah, so it's good. We're covered.
All right.
No problem. Have a great time, Miss Farmer.
Have fun.
I will. Okay. I feel like I really lost the plot of this here. But let's take a look. Shh. Please. No, we're on this reaction. So if we break this reaction down to the ions that are actually doing something, then we can look at it like this. I don't have to write carbonate in this equation because it appears on both sides unchanged. It's just a spectator. So without the carbonate, what am I left with for this reaction? Yeah, really, this is a reaction where solid sodium is hanging out in the same place as some aqueous lithium, and it says what? Yeah, so what happens? We get solid lithium, and all of a sudden now we have
It's like somebody trying to dress up as a cool kid the next day and realize they ain't dressing up the same way anymore.
And now, by the way, this brings us to a question that Kevin asked just a little bit too early, but now we can ask it. Now, do I need to worry about those twos? If there's 2 of everything, I can put that in lowest terms, right? This is correct, but we can even more easily say that solid sodium will react with aqueous lithium ions to make and there it is. In other words, what this reaction is really about is lithium stealing an electron from sodium. Right? Not the reaction we thought we got. We've always taught this as if it's sodium kicking lithium out of some kind of relationship. But really, it's lithium saying, sodium, that's a nice electron. Shame if someone took it, and bam, it takes that electron. And now the lithium's solid, and the sodium's stuck, dissolved in water, aqueous, electrons, positive neutrons.
And then carbonate's just being really bad kind of.
Yeah, and carbonate's just, that's it. Carbonate's just the friend who you thought was your friend, but was really just like, doesn't involve me, buddy. I got my lunch, buddy. I got 2 of my lunch money. Right? Like, yeah, it's along for the ride. Okay, so this is the key. When we take a reaction that we already know how to do, and we break it down to its ionic equations, we can actually figure out not just what happens, but how it happens, what the mechanism must be. See, until we started realizing what ionic equations look like, we didn't know why single displacement reactions happen. When we look here, it's really clear what happens. Lithium ions are able to steal solid sodium's electrons. When they do that, they become solid lithium, and the sodium is now positively charged and dissolved in the water. That's the actual reaction. Does that make sense? So if we take an equation that we know, we can break it down here. So let's take a look at this one. We have silver nitrate and sodium chloride. What kind of reaction is this going to be? Double displacement. And I tried to pick everything with a 1+ charge, so it'd be nice and easy. In fact, I know I picked everything with a 1+ charge, so this is a nice, easy one to switch. What do we end up with? We end up with silver chloride and NaNO3. And I'll spare you running to the solubility table. Silver chloride is not soluble. So what do I have to put here? Solid. And that means that this reaction does happen. This is a good reaction, right? Okay, so that one's real. Now again, let's turn this into a total ionic equation. And remember, in a total ionic equation, everything that's aqueous, we write them as individual ions. What are the aqueous things in this reaction? Sodium chloride is aqueous. Silver nitrate is aqueous. Sodium nitrate is aqueous. Those are all going to dissociate in water. They're going to split up. Their ions are actually free-flowing. Hey, what is not aqueous? Silver chloride. So are we going to write that as Ag+ ions and Cl- ions? No, because they are stuck together. All right? So that will not dissociate. So I want you to take a moment and write the total ionic equation for this. Break everything up into its ions. Again, I picked a nice one. There's no numbers to have to worry about. There's just one of everything. Oh my God. It was nothing. Yeah. Everything was aqueous, just like we did with this one, where we started looking for carbonate, this became lithium and carbonates, and this became sodium and carbonates. So here, this is going from sodium and chlorine, this is going from silver and nitrate, this is going from silver. Oh, this is going to not change. And this will become sodium.
So the nitrate ions stay together, or is it in nitrogen and oxygen?
Oh, good question. Nitrate is an ion, NO3. It will always stay NO3. Because the bonds inside of nitrate, like the bond that actually holds the oxygens to the nitrogen, are not ionic, they're covalent, which isn't something we've talked about, but we'll talk about that lots in grade 12 chem if you take it. But so the ion isn't nitrogen and oxygen, like that's not a bunch of separate ions. Nitrate, NO3, is an ion. It's a piece. You gotta take it as a whole. Yes, ma'am. That looks great. That looks really good. I don't have it. I'm sorry. Okay, so shall we go through this together? All right. So let's go through it all as a group, but I'm hanging out here. So let's just go one at a time. So let's start with sodium chloride. What 2 ions do we get from that? The sodium chloride is going to give us,
Oh,
well, the first ion is just sodium. Yeah, and what charge does it take? Just check your periodic table.
oh, +1.
Perfect. And that's going to be floating in water, so we say that. Okay, so the first thing we get is just sodium floating in water, right? All right, what's the next ion we get from that? I'll just keep going from the left.
Oh, for
The chlorines, right? Great. And what that Cl, what charge does it take?
negative.
Negative. Good.
Minus.
Yep, perfect. All right, so now we've taken care of sodium chloride. It's done. So what next?
What? Silver takes +1.
Yep, silver takes +1. Very good. And then this is our first radical, but NO3, right? And I stupidly wrote this with a big 3 there, but it should be NO3 like that. So NO3 is one of these, right? It's the nitride ion. NO3, and what charge does it take?
Minus.
Is it 2 minus?
Minus.
Just -1. Okay, perfect. So NO3 minus aqueous. Cool. And those all broke apart because they're all dissolved in water. And we said when you dissolve these things in water, they just break apart. But now we get to AgCl. Does it break apart?
No.
No, because it is a, what's that S stand for?
Solid.
Yeah, that's right. Solid. Yeah, it's solid. It's stuck together.
Right.
So that's just going to stay as AgCl solid. It doesn't break apart because it's solid. And then what will I get for that sodium nitrate? What's it going to do? Oh, is it dissolved?
No. Yes.
Yeah, because it's aqueous.
Yeah.
So let's just look at the ions. The first ion is Na. And what charge does it take again? That's okay. Look it up. It's on the left, far left.
Oh, +1.
Perfect. And then remember, NO3 is like from your table, from like it's a radical. And so NO3 takes what charge?
Minus.
Perfect. Perfect. Good job. Okay. How's that look? Does that look similar to what you have? So if sodium chloride's in water, that means we got a bunch of sodium ions, we got a bunch of chlorine ions. If silver nitrate's in water, it means we got a bunch of silver ions, a bunch of nitrate ions. That's the left side of this reaction. In other words, when you have a bunch of compounds in water, all the ions just flow free and flow around. But on the right side of the equation, now we have a solid compound. What's that? AgCl. It's stuck together. But what ions are still just floating around free? So sodium and nitrate. Good. So now, what are the spectator ions? What are the ions that don't actually do anything in this reaction? They just float around, getting a free ride. Yes, ma'am. And so what? Just give me the one. So one of them is NO3. So if we look here, we have aqueous NO3 ions on the left. And over here, we have aqueous NO3 ions on the right. Do they change in this reaction? No. So anything that doesn't change in a reaction, we don't write an equation. In other words, you've never written a chemical equation where it's like, don't forget to write the beaker in on the left and the right side. Right? That'd be stupid. The things that don't actually, like we don't say write the water on both sides because the water doesn't change.
But just because like it doesn't change, like it's going to meet that.
Well, that's what we're going to talk about, which is to say, if nitrate doesn't actually matter in this, in other words, silver nitrate becomes sodium nitrate, could I have picked any different ion there? Right? Like I probably could have used carbonate. I could have used, so what it tells us is that the nitrate isn't important. Now, you're right, there has to be an anion there. You have to have had an ion there that we could use. But the fact that it was nitrate is like saying it makes a difference if the taxi that gets you to the airport is a Toyota or a Ford product. That make sense? There has to be a taxi, but it doesn't matter what it is, right? In other words, if you talk about that trip you went on, you probably don't talk about the taxi to the airport unless something went horribly wrong. You hope if you go on a trip, the taxi to the airport is not something you have to talk about. Yes? Yep. What else is a spectator ion here? What else is just hanging on? Yeah. Yeah, sodium. Sodium over here is a plus charge. Sodium over here is a plus charge. So again, sodium is involved in making this reaction happen in as much as we had to use the sodium to deliver the chlorine, but sodium was just chlorine's taxi into this reaction. Nitrate was just silver's taxi into this reaction. They don't actually get involved in the chemistry. So when we break this reaction, what's it really about? What do we get?
Silver chloride.
Yeah, so the product is silver chloride, for sure. AgCl, and that's solid. And what's left on the left side of this reaction? And so what we learn from the net ionic equation is that silver ions react with chlorine ions to make silver chloride. If you ever become a chemistry teacher, which I encourage you to do, it's a good gig, all of like the junior science teachers, and they always think, because they'll always have like a reaction they're supposed to do in a lab, and they'll say like, oh, we don't have any silver sulfate to do this reaction. And you're like, take a look at that. And they're like, oh, we have silver nitrate, that'll work. And they'll be like, how did you know it would work with this other thing? And the answer is, if you understand net ionic equations, you know that this reaction is really just about silver ions reacting with chlorine ions to make silver chloride. So any compound that delivered silver ions, so all I needed was a silver compound that's soluble. Any soluble silver compound will work. And then I need to get chlorine ions. So I needed any compound with chlorine that dissolves. Does that make sense? That's what doing net ionic equations does for you. It lets you look at reactions you've always seen and understand why they work. Does that make sense? All right. Right, a net ionic reaction with sodium nitrate and magnesium chloride. So I want you guys to try this one. This one is your task for today. I want you to first write the balanced chemical equation, then the total ionic equation, then the net ionic equation. Yeah. I was trying to think of a catchy title. Nothing came to me, so I assume that at night you've always wondered what's the net ionic equation of sodium nitrate reacting with magnesium.
How do you know?
I just knew. This is like that note, there are things that keep me up. For example, I once went down a 3-month rabbit hole of like sleep deprivation because we had a soda fountain at the restaurant I worked at that no matter what cup you used would stop exactly when the cup was full. And you could use any cup in the world. It didn't matter what it was. I tried it with everything that you put a vase under this thing and press it, and when it got to the top of the vase, it would stop. You could hold it way down low, when it got to the top, it would stop. You could put a Dixie cup, when it was full, it would stop. It just didn't matter what you put in this thing. When it was full, the thing would stop. And I took it. One night I just disconnected it from the water supply and the CO2 supply. I had to take it apart. I had to see how it worked.
Did
you figure it out?
It was fascinating.
What is it put together again?
There was so much going on in there. It had something to do with electrical conductance I could tell that because there was like there was a module there that was testing, but I don't know like if there was enough laminar flow that they were able to actually send like electrical signal down the pop stream. And then to this day I can't figure it out. But man, I spent months obsessing, and now I've thought about it again, and I haven't thought about this for years. That's a really disappointing thing for me. Yeah, so I do get kept awake. And now you're gonna think about it.
I know. That's genius.
It was great, right? Because you could put like that and then do something else, and come back and grab it, put another one on, go do something else. It was a real time save. That's the question.
You're going to get one.
Coke was our supplier at the time. It was just like Coca-Cola.
Get one just for the end.
Oh no, I don't. You don't think I thought of that? I spent like 4 hours on the phone with tech support one day, and I said, "So what's wrong with the machine?" I'm like, "Nothing. You just have to tell me how." And they hung up on me. That's a true story.
I think you're really that day.
So I'm turning it into an hour equation. Would it be like 2 Na and then the like
Yep, 2 sodiums and 2.
and then I'd have to do like the plus.
Yeah, that's it. And how many magnesiums? How many chlorines? And then which of these is solid?
Maybe cool this.
Oh, this is sphere.
You say it's sphere.
Or is neither of those? See, you don't know it yet, but this is going to be a mystery of the universe that kept you up at night.
Why?
You're gonna see. You're gonna see. And you're gonna go, I get it.
I'm not gonna get it if I can't find what I told you.
Oh, none of them.
I think you're right. So I think they're all aqueous. So keep going. I think everything involved is aqueous. Left and right. I mean, check your solubility table, but I'm pretty sure everything here is aqueous.
Well, I know you have to save that by yelling.
This is double.
You have to yell out the equation and yell out the question.
It doesn't hurt. Just you did it every time.
Oh,
Yeah, you would have shot like Oh, I would need that.
Yeah, I guess those work Christmas for
When I would have people that had like write it apart, I'm like,
you do it.
oh, wait, yeah.
Okay, this is what I have for the reaction. It occurs to me, did you use chloride?
Oh,
Yeah,
yeah.
it's the same thing, just all your CLs will become ClO3s.
Okay.
It doesn't change anything. But how's that look?
I'll say yes, I can
I
tell.
use, did you use
You did nitride?
No. I, instead of using, what was it? No, instead of using chloride, I used.
Okay. I mean, well, you'd have nitrates reacting with nitrates, which is its own kind of weirdness. Yeah, that's true, but now we're going to learn why. Yeah, now we're going to learn why. So the question is, why is this no reaction? We've always said, like, oh, there's no reaction if it's not solid. But, like, that's just something I told you, right? And you believed it because you're sheep, right? Because I could tell you anything, you'd just be like, okay, whatever, I believe that. That guy got moderately okay marks in a bachelor's degree in science and then paid for a teacher's college certificate. He must know. But let's talk about why it's no reaction. Yeah, because what we end up with here is what? 2 sodiums. Yeah, a bachelor's degree is the first step in university education. And then after that, after you graduate with your bachelor's, then you get what they call graduate studies. And that's a master's degree or a PhD. So I have a bachelor's degree in sciences, and then I actually took my master's in education. So I am a master of education, in case you hadn't noticed. It means like we get like special parking spots, and like in the staff room, like those key seats where like only the masters of education can sit here. It just means I paid more. So undergraduate is getting your bachelor's degree. It's stupid naming, really, but that's what's called. Okay, and then we have Mg2 plus ions. And how many chloride ions do I have here? How many ClO3s? 2 ClO3s, cool. All right, and then on this side, what do I have? I got 2 sodiums. I've got 2 chlorates. Oh, thank you.
Why do you have to be so long? Why?
You know, I'm sure that like, I'm sure Columbus thought like, why does this ocean have to be so wide? Screw it, I'm just going home.
And that's how he found the new world. trying to get home in Noah.
And you know, there's like a whole continent of people who would have preferred if he'd thought that way. What I'm saying is it'd be better for everyone if you just quit. So now we have this, and what ions in this reaction are just spectators? Everything. We have 2 sodiums on the left, and we have 2 sodiums on the right. Nothing happens to them. We have 2 nitrates on the left, and we have 2 nitrates on the right. Nothing happens to them. We have a magnesium on the left, and we have a magnesium on the right. Nothing happens to them. We have 2 chlorates on the left, and we have 2 chlorates on the right. Nothing happens to them. So what is the net ionic equation? We start with nothing changing, and we end with nothing changing. Nothing. The reason something has to become a solid or a liquid or a gas, so that it would be a double displacement reaction that actually happens, is that there's no difference between the left side of this equation and the right side of this equation. They look different. We're like, oh, isn't sodium nitrate different than sodium chlorate? No. Not necessarily. They're all just dissolved in water. Just a bunch of ions floating. I'm not done yet. You sit down. Talking. Get to you later. All of which is to say, again, see, now I have to take a second to chastise you. All of which is to say, net ionic equations let us see under the hood of reactions and see what's really going on. If you check the OneNote, you'll find some net ionic equation homework up there. Have a wonderful day. Be kind to one another. That I also did in the classroom. Yeah, we'll do that right now.
Net equation, does it give you more work?
Yes, and then like, what is actually onto my person? You see this? Yeah. But even if
Never think about reactions the same way.
Right? Did I just change your life?
You did. You actually just changed my life.
I was trying to figure out if I did something wrong.
The way you teach reminds me of this thing on YouTube called Changes.
Game theory.
You never heard of it?
No. I mean, I've heard of game theory like as a mathematical stuff.
Oh no, this is like an entire change